More derivative practice, but this time with the Transcendentals. So going back to this sheet here, I'm going to do 4 problems for you, A, E, J, and then this other nasty thing that I made up here, the cosecant of e to the 4x squared plus 2. Horrible. But there we go. Now the point of this video is to try and show you structures of solution and a standard for work required for these types of problems. Now, these problems get a lot easier if you've memorized the derivative rules. So I'm just going to assume that you've done that. So our first is y equals sine of 3x plus cosine of 2x. Clearly I have a sum here, so we're going to start off with a sum rule. So d dx of, so we've got dy dx of, and this is going to be d dx of sine of 3x plus d dx of cosine of 2x. Now, I don't have a rule for sine of 3x, and I don't have a rule for cosine of 2x. I have a rule for sine x and cosine x. So what do we do every time that we don't have a rule for something, but we have something similar? And the answer to that is chain rule. So I'm going to do the work internally here, maybe a little work on the side, right? So what I'd like you to imagine is I'm going to let u equal 3x. I'm going to let w equal 2x. Now you can try and be clever and do something altogether, but I don't think it pays off. I'm just going to leave that work up there. So the first thing I want to do is realize I'm going to have to do chain rule for these. And so with these substitutions, what I'm going to do is I'm going to turn each term into its own chain rule. So d, and this is going to be now sine of u, and then I need that to be du, and then this is du dx. I'm going to show you another way to write this in a couple of minutes. That might be a little bit more concise. And so now this one becomes d cosine of w over dw dx. Okay? So that's what that looks like as a setup. Now, it's going to be very specific, very intentional. And calculus textbooks, just to be perfectly frank, they tend to use u, v, and w. My problem with that is my u's look like v's and my v's look like u's if I'm going fast. So I tend to skip the v. But classically, a lot of these things are written as u's and v's. So just so that you'll see that in your calculus classes, I did want to say that. So the derivative of sine of u with respect to u is cosine of u. Now, here I kind of have 2 options. If I had left, let's just say I'd done my little let work here over to the side, and then I can go du dx is equal to 3, dw dx is equal to 2. Now those are very simple derivatives, but maybe I could have done that work off to the side here. I can now just put in 3 and then plus, and the derivative of cosine of w with respect to w is negative sine w, and then this is 2, and then do my replacements. Let me move my coefficients out front so you don't think it's part of the argument of the cosine function. 3 cosine of 3x minus 2 sine of 2x. Boom, and I'm done. Let me show you another way. So this would this step would come after this step. So boom, from here. Rather than even doing the let statements, what you can say here is the derivative of sine of 3x with respect to 3x, and then this just remains 3x with respect to x, and then the derivative of cosine of 2x with respect to 2x, and then d 2x dx. Right? It's functionally the same thing, but without doing the explicit replacement. Here, this becomes cosine of 3x, because it's just treating this as a variable without doing the explicit substitution. And then this just is 3. Now, the reason why some people like this structure is because you're not introducing the new variable. You kind of are the variable of 3x, but it seems like it's one fewer step because this second derivative in the chain rule is just naturally what it is. And this is negative sine of 2x and then 2. Now, I tend to do things with little separate steps personally. This structure, though, is something that quite a number of students like, and I just wanted to show it as an option. Okay, next one is a little bit more straightforward. I've got e, which is y is equal to x squared sine of x. And I look at this and I say, oh, okay, this is all about the product rule then. So dy dx is equal to the first function, which is x squared, times the derivative of the second function plus the second function times the derivative of the first function. Oh, so this is like a simple one, right? Because this just becomes cosine of x plus sine of x times 2x. Boom, 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 done. All right, let's go on to j. I've got just a different set of rules here. I've got y equals e to the tangent of x. I mean, I have no idea if there's anything in nature that obeys that law, but that's sort of weird. So I look at this and I know that this is going to be a chain rule because, right, like I don't have a rule for e to the tangent of x. I have a rule for e to the x. So dy dx is going to equal ddx of e to the tangent of x. And so I'm actually going to do this as a little let statement and put it all together. So let u equal tangent of x, right? And so now I can come back over here and say, okay, so this becomes d e to the u du dx. I'm being very intentional about showing my chain rule. And that's the main thing, folks. If you're doing a chain rule, you have to show the chain rule, right? If I don't see two ratios multiplied by each other, you haven't shown the chain rule, right? And so now I'm going to take the derivative with respect to x, so I have something to plug into there, and that's just one of our rules, and that's just secant squared of x. Okay, the first one, derivative of e to the u with respect to u, is just e to the u. The derivative of e to the anything with respect to the thing is always e to the thing, right? And that's the glory of what the, that's the whole reason why e is e, as we talked about, hopefully. This is just secant squared of x. And then put in the replacement. E, I'm going to keep in parentheses, tangent of x, secant squared of x, and there we go. And we're done. Beautiful. All right, cool. So now, this nasty thing. I've got y equals the cosecant of e to the 4x squared plus 2. I mean, there's just like layers of complication here. The first thing is, I know that I'm going to, there's a whole bunch of things I don't have rules for. Now, what I do know I have rules for is, okay, well, if I let u equal e to the 4x squared plus 2, I know I can turn this into y equals cosecant of u. Now, there I know I have a rule, right? But the problem is I don't have a rule for e to the 4x squared plus 2. So I'm going to make w equal to 4x squared plus 2. I'm going to come over here and change this to e to the w. And now I have things that I can make rules for. Okay? So I'm actually going to do this in parts and put it together. So I know I can do dy du, and that's equal to what's cosecant of u? That's negative cosecant of u, cotan of u, right? Here, du dw is just equal to e to the w. That's just simple. And then here, dw dx is equal to, gotta do my sum rule, 4x squared plus ddx of 2, that goes to 0. This term goes to 8x. dw dx. And then I'm going to just put it all together as a chain rule then. Therefore, dy dx is equal to dy du dw dw dx. okay? And now I can multiply it all together. Negative cosecant of u, cotangent of u. This is e to the w, and this is 8x. And now let's put in our replacements back, and this thing is going to look just disastrous. Negative cosecant of, well, what's u? U is e to the 4x squared plus 2 times cotangent of e to the 4x squared plus 2. And I'm going to close parentheses, open the parentheses, e to the 4x squared plus 2, and then 8x, and I'm done. So this is a double replacement problem. So just like you just kind of work it. You could do this in the same way I did, which is like do one long chain rule, but I've seen people do just like two smaller chain rule problems as well, putting it together. But I just want to alert you to the fact that sometimes when you have a thing inside of a thing, that this is something that can happen, and just recognizing that this is a possibility hopefully will let you see it when it occurs.